So time for the final lecture part, and for this session I would like to recommend you to have access to pen and paper. If you're a PhD student, is there a possibility to Davide? Yeah. You have a pen? Great. Sending them to all technologies. Yes. Whatever works, you know, depending on circumstances. So everyone ready with pen and paper? In the meanwhile, so I'm Per, and this presentation is based on much work put in by Dr. Agin Vyas, who very recently presented his PhD thesis related to storing energy, among other things. So in this green energy project that we are involved with, which you've heard a lot about, we want to take sunlight, collect it somehow, and in some way connect several elements that can collect the sunlight, then have some kind of circuitry taking care of this power transferred from solar irradiation to some kind of electrical signal, electrical power in some format. And then eventually it's going to be delivered somewhere to something that will use this power. In order to be able to do that, we also need to think about maybe that application, whatever that might be, has a need of power which is different than the power that is actually provided by the sun. So for instance, we might have an application which wants to have power in the night, and the light comes during the day. So somehow, if we can manage to provide the power when the application wants it, we have a better solution for harvesting and delivering the power when or if needed. So a way to think about and find a solution for storing energy also is valuable and useful. So one way of storing energy is to use some form of capacitor. So the way we envisage to fabricate, manufacture such capacitors, which at the same time might be fabricated in a similar way as the kind of devices we have seen examples of here, would be to do it somehow on chip. So then we would start with some kind of wafer, like a silicon wafer. We would do some surface preparation. We would perhaps, according to Agin's results, need to do something with the surface to enable it to host appropriate materials for making these capacitors. So in this case, we need to make the surface more suitable to get this material to stick. So in this case, we want to make some kind of roughening artificially to the surface. And then we can do spin coating, and we can have a patterning of the substrate. In this case, we do lift-off process to define a metal bottom layer, which we call current collectors. So after having done a lift-off process, we have a metal pattern for contacting these capacitor devices, but we need to have an active material. So the most critical step is to put on something we call an electrode, which is part of the active material in a way in the capacitor. So with this methodology, we can put down a suitable electrode material simply by spin coating, which will facilitate making large-scale production on wafer for these kinds of devices. So I will come back to what kind of material that might be. We need to pattern that material also in conjunction with the bottom current collectors, and then we make a hard mask technique to do that. So we deposit some metal, we pattern the metal, and with that rough, tough metal, we can do electrode etching subsequently, and then we can take away this aluminum layer, in this case, that was the rough, tough mask, and we have active electrode material available for further use. So this process is some 25 steps, and we can also use this actually to build consecutively a stack of different kinds of materials when we want to build and construct this electrode. Okay, so that's a way to fabricate something that looks like this on a wafer with different kinds of geometries for these current collector and electrode patterns. So we want to make capacitors to store energy, and we call them supercapacitors, which is kind of just a fancy name. They can also be called electrochemical capacitors. And the difference, if you compare to a traditional solid state capacitor, is that you do not have a passive dead dielectric in between your contacts. So the basic material function here is that you want to have an electrolyte with ions where you can provide capacitive charge storage by moving ions in the electrolyte out to the surface electrodes. So in principle, we want to store energy by storing charge at a surface by moving ions from or within the electrolyte out to the electrode surfaces. So charge is stored at the surface, and this is in this device the way we can store energy capacitively. So we know something about the input power. Maybe we don't know that much yet about what will be required at the output. So what kind of application we would be looking at, but we know that what comes in, it's on the order of kilowatts per square meter. And then we have an excellent team of coworkers. So we are looking forward to having a very efficient conversion of this very high frequency electromagnetic radiation into a DC signal. So we can assume that we do that with a very high efficiency. But still, another question that remains is to see what level of intermittencies can we manage when we use this kind of electrochemical energy storage on chip. So let's say one idea could be that we let sunlight shine on the device during the entire day. And if we can store all that energy, we can provide the same level of power during the entire night. Is that feasible? What kind of time constant can we hope to manage with this kind of electrochemical supercapacitor storage? So that's now a question. So there will be an answer here for what we can see that might be possible if we look at state of the art today and extrapolate a little bit, how much energy we can hope to store per unit area for this kind of device. But what I would like you to do now, actually, is to try to make an estimate, to make a guess from what you have seen regarding the functionality of this kind of electrochemical capacitor. What do you think we could hope for in terms of energy per unit area for a device like this? So to begin with, each of you individually think about how to try to estimate this. in what way would you try to find out how to frame what kind of order of magnitude we could expect for energy per unit area? So individually first, think and write something, and I will give you a minute or two to do this now. You're welcome. And this, we will continue with this task. So the beginning is just your individual thinking about how to estimate this. Now, some of you have already gone further to the next step, which is very, very excellent. So now I want you to pair. I want you actually to work together 2 and 2 to try to move your thoughts further. So on this right-hand side, Andreas, can you move down to your colleague to collaborate a little bit? So now work some more. Think together, and if you can come up with an actual quantitative guesstimate for this and provide that, the group that does that, or if more than one group will do that, you will win a prize. So the next challenge, work together, and if you dare, give a quantitative measure. Unfortunately, there is a time limit. So 1 more minute, 1 more minute. So I'm very sorry to say, but time is now up in this little exercise. So thank you for your efforts. Is there a group who would like to share a quantitative guess somehow? Yes, and Andreas, your group, please share a number.
I don't know, just an estimate. So we were thinking of the Avogadro constant, just in principle.
Yeah.
Because we have ions on this, so 10 to 19, and then it's watt seconds per square meter, for example.
Okay, so your number is?
Yeah, 10 to the 19.
10 to the 19.
Watt seconds.
Watt seconds
so
per square meter.
Yeah.
So 10 to the 19 joules per square meter. It's a very, very high. It's very, very high. Yeah. Okay. Thank you. More quantitative. $50 microwatt hour. 50 microwatt hours. 50. So how did you come up with that number? Yeah. Okay, so you have seen numbers before. Yeah. Okay, that's one way of doing it. Okay, thank you. More numbers. No. So if you like, I mean, this is a possibility for thinking further in your free time about how to make a guesstimate from some kind of very basic assumptions. One way you could think about this, and I was thinking that maybe someone goes the route I went down, and to guess that on a surface, if you have ions, they have a certain size. And if you want to coat a surface with these ions, you could think that you have, well, units of charge per ion. And if you guess the size and you coat and you have one layer, you could have a start of making a guess of how much charge you could probably coat a surface with. If you go down that road, you would end up with something that is actually not as high as this. So thinking about one monolayer of charge by ions on a surface would not give you as much energy as 1 kilowatt second per square meter, or 1 kilojoule per square meter, actually. So there is some kind of trick here, which makes it possible to coat the surface per square meter with more than one monolayer of ionic charge. So what might that trick be? Yeah, there is some kind of area increase that goes on here, that you have some kind of material which is not just a flat surface, but which enhances the active surface of the electrode material. So when we want to deposit electrode materials, we want something that gives you potentially a high active surface area, a porous material. And that's one of the tricks, that we want the proper kind of porosity to have a good electrode, and to be able to coat it with a lot of charge and to store a lot of energy. So at this point, the best we can do with this kind of technology on chip supercapacitors is 1 kilowatt second per square meter. So what kind of intermittencies can we manage with state-of-the-art technology comparing to what we have in terms of power coming in? Seconds. So this is what we can hope for. So if power is out for a second, we can have that power stored on an on-chip supercapacitor of the same area as the harvesting device. One can say that, okay, if we use this state-of-the-art on-chip supercapacitors, we can manage to provide stable power on the level of perhaps a tenth of the total input power. There are more problems, so I will have you look at one other issue. So when we want to move the energy from the rectifier out to this storage unit, we can do that in principle in different ways. Hopefully we can have some degree of freedom in choosing how to do it. And if we have a choice of charging as quickly as possible or as slowly as we can to move the charge, the DC from the rectifier into the capacitor, should we do that as quickly as we can or as slowly as we can to maximize efficiency? So in principle, we can say that perhaps we can have some kind of DC-like signal on the left-hand side, and on the right-hand side, we will have a capacitor, and we definitely need to push that charge through some kind of resistance unavoidably. Should we do it as quickly as possible or as slowly as we can if we want to maximize efficiency? Slowly. Why slowly? And it's an interesting suggestion. Do we have more suggestions? There might be material issues that we need to care about for how the capacitor reacts in our case. That might be an issue. Should we look into it a little bit more in detail? The current, maybe, yeah, maybe that could be better. Let's have a quick look. So if we say that we take the fastest possible route, that would be to say that we have an immediate switch from 0 voltage to the full voltage on the left-hand side. And then we would have the optimal speed and the speed limitation by the time constant of the RC circuitry. So if we would look at the equation for that, we would say that, yeah, the current that we will have as a function of time, the loading current in that case with a step function for the voltage, would be the voltage drop over the resistor divided by the resistance. And the voltage over the resistance is the DC voltage on the left-hand side minus the voltage over the capacitor, which at the beginning is 0, but then it's gradually increasing as we charge the capacitor with the charge QC. And so with this kind of equation, we would get a description for the current as exponentially decreasing. So it would be a high current to begin with, and then it would approach 0 with the time constant equals to the RC time constant. So if we plug that into the expression for the energy, which is the integral of current times voltage, we'll have something that looks like this. So the expression for the current is inside the integral, and the voltage that we multiply that with to get the power is outside, but we can move both these outside the integral and the R outside the integral and just integrate the exponential. And between 0 and the infinity, and for infinity we get nothing, and for 0 we get minus RC, and then we get another minus sign, and in the end the total energy delivered from the voltage source would be V squared C. But then we need to look at, okay, how much energy was dissipated? What did we lose? So we calculated how much energy was delivered by voltage times current from the source side. We could just calculate the energy dissipated in the resistor, the voltage over the resistor times the current in the integral to the left. And we know the expression for the current with this charging curve. And if we do that integral, in the end, the dissipated power ends up to be half the power delivered, or half the energy delivered. So if we charge as quickly as we can with a step voltage, we will lose 50% of the energy. So if we want to have a very efficient device in total, where the storage is also used efficiently, it's not a good strategy to try to charge as quickly as possible if we want to minimize losses and have high efficiency. So we had ideas of maybe we want to do this slowly. So if we look at using a constant current source instead, we can kind of control the speed of charging here. So we need to say then for how long should we charge, and we say we charge to the same voltage as we used before, to the same top voltage. That gives us a stop time, or a total time during which we charge. And at the end, we should achieve the same amount of charge as we did in the previous case, which was capacitance times voltage. So that's determining for how long we let the constant current charge the capacitor. And in this case, we can calculate the energy delivered by saying, okay, the total voltage is the voltage across the resistor plus the voltage across the capacitor times the current, the constant current. We can remove the current from the integration, and we have an integration for up to the stop time for the both voltages across resistor and capacitor. And we can do some integration, and we will have two terms. One, the energy which is lost in the resistor, which is R times I times C times V, where the C and V, they appeared due to the fact that we have a stop time. And then we have the energy that is delivered to the capacitor. And again, a lot of letters, C's and V's come in due to the fact that we have a stop time depending on these parameters. But in the end, if we simplify this, we get an expression for the total energy delivered. So we end up with the same kind of energy in the capacitor as we recognize from previously, the capacitance times the voltage squared divided by 2. But the energy lost in the resistor now is depending on the current we use for charging. So if we just make a ratio for energy lost over total energy, we get this ratio of R times I divided by R times I plus V divided by 2. So of course, this we can make in principle arbitrarily small by making the current small. So why not make the current as small as possible? Just reducing this to the lowest we can. There will be technology limiting our choices and options here. Unfortunately, any capacitor we try to manufacture and use will not be ideal. So when modeling any real capacitor, there will be shunt parasitic conductance in parallel with that. So we need to be able to provide high enough current to not just dissipate that power we deliver through that parasitic conductance. So there is a minimum current that we can use to actually be able to charge the capacitor. But the lower we can have the current, the less loss we can have. So this is an example now of against actual materials. So what we can do is stack several different flavors of graphene derived from graphene oxide, which we reduce in different ways in the process, to have a stack of materials which would provide good enough active surface, good enough conductivity and stability, etc. So with that, we can show some net outcome in providing areal capacitance per farads per unit area, which we will want to have as high as possible, since the energy we can store is capacitance times voltage squared over 2. The higher we can make the areal capacitance, the more energy we can store. So here we have numbers of some several hundreds microfarad per square centimeter. And of course, we want to make this as high as possible. Thank you for listening. Thank you for participating. We have a group delivering a very high estimate, but daring to do so without having seen numbers before makes you the winners. So an applause to Andreas and Porter for